Hi guys, tonight we're going to explore something truly mind-bending. What if Earth had two moons instead of one? How would that second celestial companion have changed everything from the tides to the evolution of life itself, and even the course of human civilization? If you enjoy these fascinating sleep stories that explore alternate versions of our world, hit that like button and subscribe for more. And drop a comment letting me know what time it is where you are and where you're listening from. I always love hearing from you night owls around the globe. Alright, let's begin. Picture yourself standing on a beach at sunset, watching waves crash against the shore with an unfamiliar rhythm. Above you, two celestial orbs hang in the darkening sky, one brilliant and familiar, the other smaller but equally mesmerizing. This is not science fiction. This is what Earth might have looked like if our planet had captured not one, but two moons during the chaotic early days of the solar system 4.5 billion years ago. The presence of a second moon would have fundamentally altered every aspect of life on our planet, from the very formation of the first organic molecules to the rise and fall of civilizations. To understand this profound transformation, we must first consider what our current single moon contributes to Earth's delicate balance. Our moon, with a diameter of 3,474 kilometers, sits at an average distance of 384 kilometers, 1,400 kilometers from Earth. Its gravitational influence creates tides that rise and fall approximately every 12 hours and 25 minutes, moving roughly 500 trillion gallons of water across our planet's surface with each tidal cycle. Now imagine doubling this cosmic dance. Let's envision our second moon, we'll call it Lunar Minor, as roughly half the size of our current moon, with a diameter of about 1,700 kilometers, orbiting at a distance of approximately 250,000 kilometers from Earth. This smaller companion would complete one orbit every 18 days, compared to our familiar moon's 27-day cycle. The gravitational interplay between these two satellites would create tidal patterns of unprecedented complexity. The combined gravitational forces would generate what oceanographers call interference patterns, where the tidal effects of both moons would sometimes amplify each other and sometimes cancel out. During periods of constructive interference, when both moons align on the same side of Earth, tidal ranges could reach heights of 20 to 25 meters in some coastal regions, compared to the maximum 15-meter tides we occasionally see today in places like the Bay of Fundy. These supertides would occur roughly every 43 days, when Lunar Minor's 18-day orbit aligns with our primary moon's longer cycle. The complexity doesn't end there. When the two moons sit at right angles to each other relative to Earth, their gravitational forces would partially cancel out, creating neap tides of unusual weakness. Instead of the predictable twice-daily tides we know today, coastal regions would experience a constantly shifting pattern of 4, 5, or even 6 tides per day, each with varying heights and durations. The port of Rotterdam, handling 469 million tons of cargo annually, would require completely different infrastructure to accommodate these unpredictable water levels. This tidal chaos would have profoundly shaped the evolution of life itself. Scientists estimate that tidal pools, those crucial nurseries where early life first ventured from sea to land, would be exposed to air for dramatically different periods. Some pools might remain submerged for days during super tide cycles, while others could be exposed for extended periods during the complex neap tides created by the dual lunar system. Marine organisms would have evolved entirely different reproductive cycles, feeding patterns, and physiological adaptations to cope with these erratic tidal rhythms. The implications stretch far beyond marine life. Estuaries, where rivers meet the sea, serve as critical breeding grounds for roughly 70% of commercial fish species. With two moons driving more extreme tidal variations, these estuarine environments would experience salt and fresh water, mixing in patterns unlike anything we see today. The Chesapeake Bay, which currently produces about 500 million pounds of seafood annually, might support entirely different ecosystems under the influence of dual tidal forces. Consider the salmon runs that define entire ecosystems along the Pacific coast. These fish navigate upstream using tidal cues that have remained consistent for millions of years. With chaotic tidal patterns created by two moons, salmon might have evolved radically different migration strategies, potentially altering the entire food web that depends on their annual journey. The grizzly bears of Alaska, which can consume up to 30 salmon per day during peak runs, might have evolved different hunting behaviors, seasonal patterns, and even body sizes to adapt to unpredictable fish migrations. The gravitational influence of two moons would extend far beyond the oceans. Earth's crust itself rises and falls by approximately 30 centimeters twice daily due to our single moon's pull, a phenomenon called land tides that most people never notice. With two moons pulling from different angles at different intervals, the solid Earth would experience more complex deformation patterns. This additional crustal stress could influence tectonic activity, potentially altering the frequency and intensity of earthquakes in already seismically active regions. The San Andreas Fault, stretching 1,300 kilometers through California, might experience different stress patterns under the influence of dual gravitational forces. Seismologists estimate that even small changes in crustal stress can trigger earthquakes that might otherwise remain dormant for years or decades. The presence of a second moon could have fundamentally altered the timing and magnitude of major seismic events throughout Earth's history, potentially changing the course of human civilization by affecting when and where major cities could safely develop. Volcanic activity would also respond to these altered stress patterns. The roughly 1,500 active volcanoes around the world are influenced by various factors including tidal forces. Mount Vesuvius, which famously destroyed Pompeii in 79 AD, erupts on cycles that may be partially influenced by gravitational forces. With two moons creating more complex crustal stresses, volcanic eruptions might follow different patterns, potentially altering climate cycles through changes in atmospheric particle injection. The atmospheric consequences of a second moon extend beyond volcanic influences. Our current moon's gravitational pull affects not just water and rock, but also Earth's atmosphere itself. The atmosphere actually bulges slightly toward the moon, creating subtle but measurable changes in air pressure that occur twice daily. With two moons pulling from different directions, atmospheric pressure patterns would become significantly more complex. These pressure variations would influence weather systems in ways difficult to fully predict. Storm formation, wind patterns, and precipitation cycles all respond to pressure changes. The jet stream, which determines weather patterns across entire continents, might follow different paths under the influence of dual gravitational forces. The monsoon systems that bring life-giving rain to 3 billion people across South and Southeast Asia depend on predictable seasonal pressure changes. With two moons creating more complex atmospheric dynamics, these critical weather patterns could be dramatically altered. Imagine the implications for agriculture. The Indian subcontinent receives 80% of its annual precipitation during the monsoon season. If dual lunar influences disrupted these patterns, the agricultural systems that currently feed over 1.4 billion people might never have developed in their current form. rice cultivation, which supports roughly half the world's population and requires precisely timed flooding cycles, would have evolved entirely different techniques to accommodate unpredictable seasonal patterns. The changes would cascade through every aspect of Earth's climate system. Ocean currents, driven partly by tidal forces, distribute heat around the globe and regulate regional climates. The Gulf Stream, carrying 25 times the flow of all the world's rivers combined, helps maintain Europe's temperate climate. With two moons creating more complex tidal patterns, ocean circulation could follow dramatically different paths, potentially leaving London with a climate more like that of northern Canada, despite being at the same latitude as Calgary. These climatic shifts would have profoundly influenced the evolution and migration of early humans. Our ancestors developed agriculture approximately 10,000 years ago, during a period of relative climate stability. If dual lunar influences had created more chaotic weather patterns, the consistent seasonal cycles that enabled the development of farming might never have existed. Without agriculture, human population would likely have remained at the few million individuals that hunter-gatherer societies can support, rather than reaching our current 7.9 billion. The intellectual development of humanity would also have taken different paths. Many early civilizations developed sophisticated astronomical knowledge by observing lunar cycles. The Mesopotamians created the first calendar systems based on lunar months, leading to advances in mathematics and timekeeping that formed the foundation of modern science. With two moons following complex orbital patterns, early astronomers would face far greater challenges in developing predictive models for celestial mechanics. However, this complexity might have accelerated certain aspects of mathematical development. The need to predict the positions of two moons, each following different orbital periods and creating complex interference patterns, could have driven earlier development of sophisticated mathematical techniques. Ancient cultures might have developed calculus-like methods centuries earlier than they actually did, driven by the practical necessity of predicting tidal patterns for navigation and coastal settlements. The cultural impact of two moons would be immeasurable. Lunar symbolism permeates virtually every human culture, from the crescent symbols of Islam to the lunar calendars used in Chinese and Jewish traditions. Many cultures associate the moon with femininity, fertility cycles, and the passage of time. With two moons in the sky, human mythology and religious systems would have developed entirely different symbolic frameworks. Consider how different literature and poetry might have become. The romantic associations of moonlight, the metaphors of lunar phases representing life cycles, the very language we use to describe beauty and mystery. All of this would be fundamentally different with two celestial companions gracing our nights. Shakespeare's Juliet might have been compared to two moons shining in the darkness, and the phrase, "once in a blue moon," might refer to the rare occasions when both satellites appear blue due to atmospheric conditions. The navigation techniques that enabled human exploration and trade would have required entirely different approaches. Polynesian navigators, who colonized islands across the Pacific using traditional wayfinding methods, relied partly on lunar positions to determine their location at sea. With two moons following complex orbital patterns, navigation would demand far more sophisticated understanding of celestial mechanics. This might have delayed oceanic exploration by centuries, or alternatively, it could have forced earlier development of more advanced navigational tools and techniques. The implications for modern technology would be profound. Our current satellite communication systems rely on precisely timed orbital mechanics. The presence of a second moon would create additional gravitational perturbations affecting satellite orbits, requiring more complex calculations for space missions. The Apollo program, which successfully landed 12 humans on the Moon between 1969 and 1972, would face the additional challenge of choosing which moon to visit and dealing with the complex gravitational interactions between both satellites. Tidal energy, which currently generates approximately 250 megawatts of electricity worldwide, could potentially produce far more power, with two moons creating stronger and more frequent tidal cycles. Countries like South Korea, which plans to generate substantial electricity from tidal power, might find themselves with access to far greater renewable energy resources. The Siwa Lake Tidal Power Station, currently the world's largest at 254 megawatts, might be dwarfed by installations designed to harness the power of dual lunar tides. The psychological effects on human behavior represent another fascinating dimension of this alternative Earth. Numerous studies have attempted to correlate human behavior with lunar cycles, though scientific consensus remains divided on the strength of these connections. Emergency room visits, births, sleep patterns, and even crime rates have all been studied in relation to lunar phases. With two moons creating more complex gravitational and lighting patterns, human circadian rhythms and seasonal behaviors might have evolved quite differently. Sleep cycles, which are regulated partly by light exposure and may be influenced by gravitational forces, would adapt to the complex interplay of two moons. Some nights might be illuminated by both satellites, creating brightness levels significantly higher than our current full moon, which provides roughly 1/4 of a lux of illumination. Other nights might see both moons in their new phases, creating darkness deeper than any we currently experience. Human eyes and sleep patterns would have evolved to cope with these dramatic variations in nighttime lighting. The animal kingdom would show even more dramatic adaptations. Many species rely on lunar cues for reproduction, migration, and feeding behaviors. Grunion fish, which spawn on California beaches during the highest tides following full and new moons, would need entirely different reproductive strategies to cope with unpredictable tidal patterns. Sea turtles, which have used lunar cycles to time their beach nesting for millions of years, might have evolved completely different nesting behaviors, or even different reproductive cycles altogether. Nocturnal predators that rely on lunar illumination for hunting would face dramatically different conditions. Owls, which can hunt effectively during partial lunar illumination, would experience nights ranging from brilliant double moonlight to complete darkness. Their hunting strategies, prey relationships, and even physical adaptations like eye size and feather patterns for silent flight might have evolved differently to cope with these variable conditions. The formation of Earth's second moon would depend on the specific circumstances of the early solar system. Our current moon likely formed from debris created when a Mars-sized object called Theia collided with early Earth approximately 4.5 billion years ago. For Earth to have captured a second moon, several scenarios are possible. Another major impact could have created additional debris that coalesced into a second satellite. Earth might have captured a large asteroid or small planet that wandered too close, or the original impact might have been more complex, creating multiple large fragments that became separate moons. Each formation scenario would result in different orbital characteristics for our hypothetical lunar minor. A captured asteroid might orbit in a more eccentric or inclined path, creating even more complex tidal patterns. A moon formed from the same impact that created our familiar satellite might orbit in a more circular, predictable path, though still creating the interference patterns that would dramatically alter Earth's tidal systems. The long-term stability of a two-moon system presents interesting challenges. Gravitational interactions between the moons themselves would cause their orbits to evolve over geological timescales. Computer simulations suggest that two moons might either gradually move apart until one escapes Earth's gravitational influence entirely, or they might eventually collide, creating spectacular fireworks visible from Earth's surface and potentially showering our planet with debris. This orbital evolution would create gradually changing tidal patterns over millions of years. Species that adapt to specific tidal cycles might face extinction as orbital mechanics slowly alter the very environmental conditions that shape their evolution. Alternatively, the gradual nature of these changes might drive accelerated evolution as organisms continuously adapt to slowly shifting tidal patterns. The geological record of such a system would be fascinating to decode. Tidal rhythmites, layers of sediment deposited by ancient tides, currently help scientists understand how the moon's orbit has changed over geological time. With two moons, these sedimentary records would show far more complex patterns, potentially making it more difficult for future geologists to decode Earth's tidal history, but also providing a much richer record of orbital mechanics. Coastal erosion patterns would create dramatically different landscapes. The varied tidal ranges would carve coastlines in ways unlike anything we see today. Some areas might experience extreme erosion during supertide periods, while others might see unusual sediment deposition patterns during the complex neap tides created by dual lunar influences. The White Cliffs of Dover, carved by thousands of years of consistent tidal action, might have entirely different shapes and compositions under the influence of chaotic dual tides. The impact on coral reef development would be profound. Coral reefs, which currently support 25% of marine species, despite covering less than 1% of ocean area, depend on specific tidal patterns for nutrient flow and reproductive cycles. Many coral species spawn during particular lunar phases, releasing eggs and sperm in synchronized events triggered by lunar cues. With two moons creating unpredictable lighting and tidal patterns, coral reproduction might follow entirely different cycles, potentially resulting in reef ecosystems with different species compositions and structures. Ice Age cycles, which have shaped Earth's climate for millions of years, might also be affected by a second moon. These cycles are driven partly by changes in Earth's orbital characteristics and axial tilt, known as Milankovitch cycles. The gravitational influence of two moons could alter how Earth's rotation and orbit evolve over time, potentially changing the timing and intensity of ice ages. The last ice age ended approximately 11,700 years ago, enabling the development of agriculture and civilization. If dual lunar influences had altered ice age timing, human development might have followed entirely different timelines. The philosophical implications of living under two moons extend beyond practical considerations. Human cultures have always found meaning in celestial patterns, using astronomical observations to develop concepts of time, cycles, and our place in the universe. The complex dance of two moons might have led to entirely different philosophical and religious frameworks. Concepts of duality, balance, and cosmic harmony would likely feature more prominently in human thought. Mathematical concepts might have developed differently as well. Early human counting systems often incorporated lunar cycles, leading to base 28 mathematical systems in some cultures. With two moons following different cycles, early mathematicians might have developed more sophisticated number systems much earlier, potentially accelerating the development of advanced mathematics by centuries. The seasonal patterns that govern so much of human activity would be far more complex. Agricultural societies developed around predictable seasonal changes in temperature, precipitation, and daylight hours. While two moons wouldn't directly alter these solar-driven seasons, their influence on weather patterns, ocean currents, and atmospheric circulation could create more chaotic seasonal variations. This might have prevented the development of large-scale agriculture altogether, keeping human populations small and nomadic. Alternatively, the challenge of predicting more complex seasonal patterns might have driven earlier development of sophisticated weather prediction and agricultural planning techniques. Civilizations might have become highly advanced in mathematical modeling and observational astronomy out of sheer necessity for survival. The energy balance of Earth's climate system would face additional complexity from two moons. While lunar influences don't directly affect the amount of solar energy Earth receives, they do influence how that energy is distributed through atmospheric and oceanic circulation patterns. The more complex tidal patterns could create different heat distribution patterns, potentially altering global temperature gradients and storm formation patterns. Coastal cities, which currently house roughly 40% of the world's population, would face entirely different challenges and opportunities. Venice, which already struggles with regular flooding due to high tides and sea level rise, would require radically different engineering solutions to cope with unpredictable super tides reaching heights of 20 meters or more. The Netherlands, which has managed water levels for centuries using sophisticated engineering, would need to develop far more complex flood control systems to protect its 12 million inhabitants from chaotic tidal patterns. However, these challenges might also present opportunities. Coastal cities might develop into sophisticated floating settlements capable of rising and falling with extreme tidal ranges. Architecture and urban planning would evolve entirely different approaches, creating cities that could adapt dynamically to changing water levels rather than fighting against them. The global economy would be fundamentally different as well. International shipping, which currently moves over 11 billion tons of cargo annually, relies on predictable tidal patterns for port scheduling and navigation. Ships entering major ports like Shanghai, which handles over 47 million containers per year, would face dramatically more complex logistics challenges. The precise timing required for container loading and unloading would need to account for unpredictable tidal windows and varying port depths. Fishing industries would adapt to entirely different seasonal patterns. The Grand Banks off Newfoundland, historically one of the world's richest fishing grounds, might support completely different fish populations adapted to chaotic tidal mixing patterns. The annual migration patterns that currently support fishing industries worth hundreds of billions of dollars globally might follow entirely different routes and timing. Tourism industries would develop around the spectacular sight of two moons in the night sky. Locations offering the best views of dual lunar eclipses, occasions when Earth's shadow passes across both moons simultaneously, would become major destinations. The frequency of lunar eclipses would roughly double, creating more opportunities for astronomical tourism, but the complex orbital mechanics would make these events more difficult to predict accurately. The study of astronomy would have developed along entirely different paths. Ancient astronomers in Babylon, Egypt, and Greece developed early mathematical models by observing and predicting lunar motions. With two moons following complex orbital patterns, ancient astronomers would face far greater challenges in developing predictive models. This might have delayed the development of mathematical astronomy by centuries, or it could have accelerated the development of more sophisticated mathematical techniques. Johannes Kepler's laws of planetary motion, developed in the early 1600s, were partly inspired by careful observations of planetary and lunar orbits. With two moons providing more complex gravitational data, astronomers might have developed more advanced understanding of orbital mechanics much earlier, potentially leading to earlier development of spaceflight and satellite technology. The tidal heating effects that warm some of Jupiter's moons through gravitational flexing would create additional geological activity on Earth. While Earth is too large to experience the extreme tidal heating seen on Io, Jupiter's volcanically active moon, the additional gravitational forces from a second moon would create more crustal flexing. This could result in increased geothermal activity, potentially providing more renewable energy sources but also creating more seismic instability. Hot springs, which currently provide renewable energy in countries like Iceland and the Philippines, might be more numerous and powerful with additional tidal heating from two moons. Iceland currently generates roughly 25% of its electricity from geothermal sources, and similar resources might be available in many more locations with increased crustal heating. The evolution of technology for measuring and predicting tidal patterns would have advanced much more rapidly. The challenge of creating accurate tidal tables for navigation would have driven earlier development of sophisticated mathematical modeling techniques. Mechanical computers, similar to the ancient Antikythera mechanism but far more complex, might have been developed centuries earlier to handle the computational challenges of predicting dual lunar influences. Modern GPS systems, which currently require precise understanding of gravitational effects to maintain accuracy, would need significantly more sophisticated algorithms to account for the additional gravitational perturbations from a second moon. The constellation of 31 satellites that currently provides global positioning services would require constant orbital adjustments to maintain accuracy in a more complex gravitational environment. The development of lunar bases and space exploration would face the interesting question of which moon to visit first. The closer proximity of Lunar Minor would make it a more accessible target for early space missions, but the larger mass and more familiar orbit of our primary moon might make it more suitable for permanent settlements. Space agencies would need to develop entirely different mission planning approaches to account for the gravitational interactions between both moons and their effects on spacecraft trajectories. Mining operations on both moons could provide resources for Earth-based industries or space-based manufacturing. The estimated value of rare Earth elements on the moon is calculated in quintillions of dollars, and a second moon would potentially double these resources. However, the complex orbital mechanics would make transportation between the moons and Earth more challenging and expensive. The biological rhythms that govern life on Earth would show remarkable adaptations to dual lunar cycles. Many marine organisms currently synchronize their reproductive cycles with lunar phases, taking advantage of specific tidal conditions for spawning. With two moons creating unpredictable tidal patterns, these species might have evolved internal biological clocks capable of tracking multiple overlapping cycles, or they might have abandoned lunar synchronized reproduction altogether in favor of other environmental cues. Migratory animals that use lunar cues for navigation would face particular challenges. Some birds are thought to use lunar polarization patterns for navigation during their journeys, covering thousands of kilometers. With two moons creating more complex polarization patterns in the night sky, these navigation systems might have evolved to be far more sophisticated, or animals might have developed entirely different migration strategies based on other environmental cues. The cultural celebrations and festivals that currently revolve around lunar cycles would be dramatically different. The Chinese New Year, which follows lunar calendar patterns and affects the schedules of over 1 billion people, might be celebrated at entirely different times with two moons following separate orbital cycles. Religious observances like Ramadan, which begins with the sighting of the new moon, would require more complex astronomical calculations to determine proper timing. Timekeeping systems would have developed along entirely different lines. Many cultures developed calendars based on lunar months, creating the foundation for modern timekeeping systems. With two moons following different orbital periods, early calendars might have been far more complex, potentially leading to earlier development of sophisticated mathematical approaches to time measurement, or alternatively, creating more fragmented and locally specific timekeeping systems. The romantic and artistic inspirations drawn from moonlight would be enriched by the presence of two celestial companions. Poets and artists would have access to far more varied nighttime lighting conditions, from the brilliant illumination of dual full moons to the subtle interplay of crescents at different phases. The development of nighttime activities, from evening festivals to outdoor work that takes advantage of natural lighting, might have evolved differently with more varied and sometimes more intense moonlight available. As we contemplate this alternative Earth with its dual lunar companions, we begin to appreciate how profoundly our single moon has shaped not just our planet's physical systems, but every aspect of life as we know it. The complex tidal patterns, altered climate systems, and different evolutionary pressures would have created a world both familiar and alien, where humanity itself might have taken entirely different paths towards civilization, technology, and understanding of our place in the cosmos. In this dance of two moons, we see reflected the delicate balance that has enabled life to flourish on our own world, and gain deeper appreciation for the precise cosmic circumstances that have shaped our remarkable planet.